Cloud, okay. We are recording. Welcome to another exciting computer architecture class. Let's see where we are with this. And let's see how far up I can go. Let's see how far this way I can go. All right. So welcome to another exciting computer architecture class. In our last very exciting computer architecture class, we were covering homework 3, along with threading, superscalar, and concurrency concepts. Let's talk a little bit about threading versus concurrency. I'm thinking of the word multi. Multi is a prefix which we often use when we describe things like multi-threading or multi-processing, which is a synonym for concurrency. But what is the difference between multi-threading and multi-processing? What is concurrency instead of threading? How do I know? These are different things. Yes, sir.
Would multi-threading be in the same core, but multi-processing be two different CPUs?
Very interesting. Multi-processing, different CPUs, threading, same core. How about this? Multi-threading, multi-processing, and how about another one I'm going to use called multitasking? Ooh, a lot of multi going on here. Multi with an I, multi. So, sounds like someone's saying, well, to have concurrency with multi-processing, you use two different cores. That sounds good. What if I have a network of workstations and they were all single core machines? Wouldn't that be also true concurrency? Because they could all do things at the same time. So true concurrency enables multi-processing. But if I have one core, I can still have multi-threading and I can still have multitasking. But with just one core, the only kind of concurrency I can envision might be through superscalar processing, which is not considered multi-processing and is not considered true concurrency. So that's interesting. What's the difference between multi-threading and multitasking? These are different, right? Any computer scientists in this room? We've got one here. We should know the difference if we're computer scientists or even if we're just knowledgeable about computing. Let's think about this. Does anybody use Windows? Show of hands. Windows? Oh, that's good. 2, 3, 4. 4 people, 5 people use Windows. Anybody use a Mac? We got 2 people use a Mac. That's good. How about Unix? Anybody use Unix? What you got the Dell? What are you using on that Dell?
Windows.
Oh, you just don't raise your hand. Okay, if you don't vote, raise your hand. That's you. So what you want to do is, but you didn't raise your hand because you don't vote. So what I'm thinking here is that Unix, Mac OS, which is it's really a Unix variant, Windows, and I don't know what other operating systems I can think of. That's about it. That's all I know. Oh, maybe iOS are all, I'll call it multitasking operating systems. How do I know? Well, they all have task managers, right? How do I get there? Alt, Control, Delete, say hi to the task manager. What is it showing me? All these different tasks. What's a task? I know what multi means. It's like more than one, right? Multi, lot. Or several. What's a task? I don't know what a task is. Yes, you look like you're about to raise your hand, but it's not quite getting there.
It's just something running on your computer.
Something that runs. Well, I guess a thread can run, but it's not a task. So let's think about this. Multitasking in a computer is the idea that you have a round-robin scheduler which uses a priority queue to allocate resources. There are two basic kinds of resources we care about when we are dealing with a CPU. We care about time and we care about space. And that's it. Space and time are the two things we trade off all the time. So one of the resources we're going to allocate is some kind of storage, RAM, disk space, virtual memory space, something out there where we're going to store the so-called task, task 1, task 2, task 3, through task n. Each time we switch from one task to another, we have to take the existing task and save it to our virtual memory. If the virtual memory is a mechanical drive, saving speed could be done in access times measured in milliseconds. It could be really slow. If you're trying to do processing on a 1 megabyte image using Photoshop, it might not take that long to save it. But what if you do 10 megabytes? It could take 10 times longer. What if you do 100 megabytes? 10 times longer than that. Suppose you did a gigabyte or 2 gigabyte image. Well, it's just going to take a long time to save. Moreover, the amount of time it takes to save out to virtual memory and then switch your context to swap in from virtual memory and start running task 2, that's all part of the CPU time that's been allocated to the individual task. If you spend more time swapping out and swapping in than you spend on the process itself, then you are said to be thrashing. You're thrashing in memory. And this virtual memory thrashing comes about because each task has memory that is protected relative to the other task. Why on earth would anybody want to protect memory? What are we protecting it from? Terrorists? And the answer is, well, we're protecting it from our own dumb selves. Because what happens in some programming languages is people can do things like this, $p int, which allows p to be a pointer to an integer. And then you have direct access to the addresses. That's what happens in C and in C++. And when that occurs, that means you can mangle the data and you can mangle the program, because in von Neumann style computing, programs and data are geographically co-resident in the same RAM. It's not true for Arduino. In Arduino, we put the program memory aside in double EEPROM, so it starts right away when we come up from no power. But for regular computers like the desktops that we use in Windows and Mac and Unix, we can do stuff like this. We can overwrite an array and then keep going and go right into memory and crash the task. But that's okay from the operating system point of view, because if task 1 crashes, it's got protected memory address space, so it crashes it goes goodbye, but the other tasks continue to run, and the operating system does not crash. So protected memory affords us a kind of protection, but it isn't free. It costs. It costs space. It costs time. I gotta use space in my virtual memory that's gonna be like out in the hard drive somewhere or solid state disk. And then I gotta do something about taking time to swap out and then swap in. This is called a high overhead context switch. And it comes with real life examples. Let's consider, for example, I'm working real hard. I got my stuff, I'm at my desk, and the boss comes over, pointy haired boss, and he throws this on the desk and he says, "This is your top priority item. I need you to do this right now." I drop everything I'm doing. I say, "Yes, sir." And I start working on it. Sometime around 2 in the afternoon, I'm done. I say, "Here it is. It's all done." He says, "Good. Get back to work." You're welcome. So now I'm back at my desk and I go, "Where was I? What was I doing?" I got interrupted. That's a high overhead context switch. This happens all the time. You're working away, you get an interrupt. It comes in the form of a phone call. It's ring, 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 ring. You go and you say, "Hello?" And it says, "Your warranty period is up and you've got to renew it right away or else your car's going to fall apart and all the wheels are going to fall off." And I'm like, "God, why can't I get these people to stop calling me?" And you block the number and they go and try another number. And you keep answering it because you're a fool. And you keep thinking, "Oh my God, it could be something important." And it's always some idiotic telemarketer. You're getting interrupted. And the overhead in the context switch is pretty high. High overhead context switch, resources involving extra memory, swapping memory out, swapping memory in. All of these things are prices that we pay in order to have a robust and reliable operating system. That's what a multitasking operating system gives us. It's also what it takes away, right? It doesn't give it to us for free. Now comes multi-threading. One of these tasks could have thousands, indeed tens of thousands of these threads, all running inside of the task. And the characteristic of the threads is no protected memory. They still have a round-robin scheduler. They still have priority. They can even group the threads. And you can experience this if you get into thread programming in Java. However, without protected memory, that means the threads in the task that you're writing a program for all have to play nice together. But that's okay, because it's your task. And if your task crashes because they step on each other's toes, well, that's your problem. So we gave you a great big powerful gun, and we let you shoot yourself in the foot, pow! And you go, "Oh, my toes hurt." So stop shooting yourself in the foot. But that's what multi-threading does, because now when I switch from one thread to another, I don't have to worry about protected memory. I assume everybody's sharing memory. And if everybody's sharing memory, I have a low overhead context switch. And that's why I can run thousands and thousands of threads. Initially, when people had CGI interface for their web server, they used to write Visual Basic programs on the server. Every time they had a visitor, it would create a new task. Let's think about this for a minute. Everything works great for 10 visitors, 20 visitors. Then you go live and you get 1 million visitors. Calvin Klein goes live during the Super Bowl, they get 10 million visitors. The whole system goes crashing down. And Microsoft says, "Oh, you need a bigger computer." Right? Why? Because you can't run 10,000 or even 1 million tasks on a Windows machine without crippling it. But if you have multi-threading, then every time somebody comes and visits your web page, you start a new thread of execution which services that visitation. It gives you a socket server, opens up a socket input, starts to do processing, outputs to a socket output, and now all of a sudden you've got a small thread that uses shared memory with all the other threads and can handle a lot more clients. So multi-threading is a big win, assuming you can get the threads to cooperate without stepping on each other's toes. And it's a big win because you can have lots and lots of threads running inside of a single task, and they can all share the resources of that task. And as they consume more and more memory, it's from that task. That's the difference between multitasking and multi-threading. But what about concurrency? Well, that, again, is different. True concurrency means two things actually happening at the same time. Whereas if you think about multitasking and multi-threading, they're simulating concurrency. It's not true concurrency because these two things are not happening at the same time. The round-robin scheduler is allocating resources one task at a time. Same thing within a task if you have a round-robin scheduler for multi-threads. That's the difference. Sometimes people call true concurrency multiprocessing. And indeed, it is the correct analysis that you must have more than one CPU in order to make that happen. A multi-core processor is certainly one way to do it. A network of workstations is another. How am I doing here so far? Is it clear? Yes, sure. So what about that homework 3? You got any questions about homework 3? I think it's going to be due. I forget exactly when. I think it's the end of the day Thursday. Isn't that right? Yeah. So that's good. We've got a real nice homework coming up. I think you're going to know all about SSD, SISD, SIMD, MIMD, and MISD. So this is going to be Flynn taxonomy. That's what we covered. Let's see what else we have. We did tri-state logic. That's good. And we talked a little bit about RAM. And we did some row reduction, and we talked about Darlington transistors. And I think that gives us good coverage on homework 3. And seeing that there's no questions, I think what I'll do is
Professor.
Yes, sir.
I have a question on homework 3.
Oh, go right ahead.
Question number 4.
Question number 4. Question number 4. Oh, here we go, multi-threading. We got a multi-threading question. A multi-threaded system has a low overhead context switch. This is because it shares memory with other threads. True or false? Does a multi-threading operating system share its memory with the other threads? Is it a low? Yes, yes, of course. We just went through that. So in other words, the difference between multitasking and multi-threading is the threads will run inside of a single task and they all share memory with one another. And that's why it has a low overhead context switch. Does that answer your question?
Yes.
Yeah, very good. Thank you. Any other questions out there in Zoom land? Zoom land, any questions on homework 3? No? Okay. Very good. Very good. Moving on. Onward and upward. You know, I could almost see, if most people want to do distance learning, I could see bringing in the other section. You know, for those individuals who want to come in, because I think we could have more people in this classroom, depending on how many people want to do the distance learning thing. So anyways, what I thought I would do is give you sort of the big picture overview of computer architecture and then give you a drill down. Here is your typical von Neumann style architecture. You got your memory. And in von Neumann style architecture, memory is used for both programs and data. There's some kind of a finite state machine we'll call the control unit. And it uses something called an arithmetic logic unit, which is going to do some elementary processing, maybe floating point processing, but not necessarily. The control unit and the memory can all reside in the same chip. In fact, in the Arduino, they do, but in the case of larger desktop computers, the central processing unit is separated from main memory. And so what we do is we call this part the CPU for most desktop computers. But if you're doing a microcontroller, it'll have the memory kind of built in as well. And it's a slightly different architecture. And then we're going to have input and output. As separate subsystems into and out of the CPU. Prior to this invention of an architecture, there was a computer, probably the first general purpose electrically numerical programming computer, general purpose programming computer, called ENIAC. And ENIAC had about 18,000 tubes. I had the pleasure of visiting its accumulator in the Smithsonian Institution a couple of summers ago. Turns out, with ENIAC, to do the programming, instead of having memory for programs, he had memory only for data. Why would you have memory only for data? Well, because to get electronic memory before the invention of transistors, you needed to have a switch that would run fast, but because it wasn't a transistor, it had to be a tube. So this would be vacuum tube-based memory. Tubes, or what the British call valves. And then, to program the ENIAC, they would use patch cords. And so this patch cord-based system was considered a non-von Neumann architecture, because von Neumann came around and said, no, I want the programs and the data to reside in the same place. ENIAC didn't know that, didn't do it. And in fact, I don't think they could have afforded to do it, because even though patch cords were used for programming, they still needed 18,000 tubes. And if you think about it, we have billions of transistors in our cell phones. So getting by with a computer that has only 18,000 switches is kind of a neat trick. And knowing this, as I do, it is the answer to homework number 3. No, homework number 4, problem 3. This is actually part of question 3 in homework number 4. That's kind of good to know. Let's see if we can do another little bit of some computers do not have multi-threading, they don't have multitasking, and they don't have true concurrency. These computers, believe it or not, make up the majority of the computers we encounter. They're embedded computers. Embedded means they're built into something or other, and they're dedicated to the task. So for example, I've got a little mouse over here. Here's my mouse. It's got a small computer in it. It's embedded into this mouse. You don't see the mouse computer unless you pull open the case. You never program the mouse computer. It does one thing, transmits data through Bluetooth into this computer over in here, so that you can proceed to use this as a PIC device. This is a low-power, networked embedded system. Actually, it's not even networked. I'll just say it's using a point-to-point protocol with Bluetooth. So that's an interesting example of a computer, right? How about this keyboard? Same thing. This keyboard's got a computer in it. and a wireless transmitter that allows it to communicate keystrokes. So that's a computer that's scanning the keys, transmitting data into this other computer, another networked system. Well, not quite networked, point-to-point protocol. It's a digital data communication system, for sure. These computers run without any form of multitasking, and yet they still simulate a kind of multitasking. And the way they do that is they're able to obtain what are called interrupts. And interrupt control can come either from internal or external sources. So internal to the CPU, you could have timers. Or external to the CPU, you can have wires. Those wires come in, perhaps from a multiplexer coming in from these keys, and every time you press a key, it generates an interrupt. That interrupt causes the present state of the CPU to be pushed into a stack. It then jumps to the interrupt, services the interrupt, returns from the interrupt, and then proceeds to continue doing whatever it was doing from before. So perhaps every time you press a key, it goes through a scan process where it scans all the keys, encodes which keys are depressed, then returns from the interrupt and transmits that out to the computer. So interrupt control enables external asynchronous devices to cause some kind of an action in the CPU. The external world, these are the things like the buttons you press on the keyboard, these are asynchronous. Asynchronous external interrupts. Interrupts are so valuable. You need interrupts. Why? Why? I mean, I hate being interrupted. Don't you hate being interrupted? But what if you didn't have an interrupt? What would be an example? How about this phone? I wonder if anyone's calling me. Hello, is anyone there? No? I better check back later. Hello, is anybody there? There's still nobody there. Nobody likes me. Wait, is anybody there? No, nobody's there. So what happened? I decided to start polling the phone. That's very inefficient. It means I have to keep checking the phone to see if anyone's calling me. That's not good. I don't like that. The ringer on the phone, believe it or not, is the feature that makes it useful and annoying. Because if the phone didn't ring, you'd never know if anybody wanted to call you. You have to get interrupted. Because your phone is useless if you have to keep looking at it to see if anyone's calling you. So interrupts are important. And they're important for the CPU too, because it can't just keep scanning to see if a key is being pressed. That's a waste of the CPU's time. It needs an interrupt to come in so that it can go scan the whole keyboard in a nanosecond or 2 or 10, and then come back and then encode it and do the transmission out without being interrupted, because people are generally typing slow relative to the computer. And the memory. Well, the memory can be divided up into several different sections, right? There could be some RAM, some ROM, and perhaps something even slower, like a disk drive or an SSD. Moreover, I/O devices. I/O devices can either be directly addressed through their I/O bus. This could be, for example, a software peripheral interface bus, SPI bus, or we could have something that allows people to write directly to memory, direct memory access. So I can have DMA devices, direct memory access devices, deposit large blocks of data directly into sections of memory and then make it available. And that separate register can be available for something like images that come in from a large graphics buffer, let's say out of a camera, and dropping right into computer memory. That's a distinct possibility. You can have that. suppose the timers are integrated in with the CPU. Those timers don't necessarily run on the same clock as the CPU clock. So the timers too can give us an asynchronous input. And what you can do with the timers is interesting. For example, I have one application in my class where I sample from the A to D converter and then output to a digital to analog converter. I want that sampling to be uniform. Uniform sampling means it's got to happen every 25 microseconds. Another sample comes in, another sample goes out. A non-uniform sampling system would do me no good because I write my programs to assume uniform sampling. Well, as it happens, in between samples, 25 microseconds, I got a lot of time. And that's where I do my digital signal processing. So what happens in Arduino land is you do a setup, then you attach your interrupt. And it could be an external interrupt, just fine. Then your main loop does your processing. And then somewhere in here, the external interrupt is serviced by a separate subroutine, hopefully one that doesn't take too long. And then you have an opportunity. Inside of that interrupt, you have an opportunity to get interrupted again. And you can nest the interrupts. Or if you think it's critical and you don't want to let anybody else interrupt you while you're busy being interrupted, you can mask the other interrupts. So you can control how interrupts come in. So if an external source gives me an interrupt, is it synchronous with respect to the CPU or asynchronous? You tell me. Repeat the question, sure. So here comes an external interrupt, external to the CPU, right? What could it be? Well, it's probably me typing on my keyboard over here. Is that synchronous or asynchronous? Is it in time with the CPU clock or is it out of time with the CPU clock? It's asynchronous, right? Because the CPU clock does whatever it does, and I do whatever I do, and I don't care what the CPU is doing. I'm going to type as fast as I want to type. So external interrupts are asynchronous with respect to the CPU. And that's the answer to question 14 in homework 4. Peripherals come in. The input and output bus, right? Think about it a different way. You can have all kinds of I/O, right? Here comes one, USB. Here comes another, serial programmer interface. Here comes a third, I2C. Here comes a fourth, maybe PCIe, PCI Express. Right? All this different I/O comes out of the CPU. Yes, it's in the box. Okay, maybe there's a slot and you can plug your card in, but it's still external to the CPU. You put a graphics card in, even a fancy one like the NVIDIA graphics card, it's external to the CPU. At least the main desktop CPU, even though it may have a number of different interesting and wonderful CPUs. Now, if you remember last time we had a discussion about ARM versus NVIDIA versus Intel, and we said, and AMD, and why are these all different, and how come they have different business models? But if you've been following the news, NVIDIA is in the process of taking over ARM and spending, I think it was $11 billion to do it. Now, it may not pass muster with the Justice Department, nobody knows. But the general word on the street is this is going to go through. And it's going to take out one of the major competitors. NVIDIA is really a hardware company, but it outsources all the fabrication for its semiconductors. So it is a fabulous semiconductor manufacturer. But it does make, it OEMs big systems. Once it gets its hands on ARM, it'll have all the intellectual property associated with that. One of the most powerful synergies to come across the computer architecture world. And those who are paranoid may be really worried about what happens next. And as Andy Grove said, who used to be the CEO of Intel, only the paranoid survive. So let's think about this. Arduino is an interesting architecture because it's different from the von Neumann architecture. It not only has RAM and ROM and memory, but it also has double EEPROM. Let's take a word or two about this idea of different kinds of memory. Well, what does RAM stand for? Random access memory. What's ROM stand for? Read-only memory. What's double EEPROM stand for? Oh, really? What does PROM stand for? PROM is programmable read-only memory. So you could program it. How can you do that? How can you program it? Well, you can program it at the factory, or you can program it just once. Then there's another form of memory called EEPROM. EEPROM is erasable programmable read-only memory. With erasable programmable read-only memory, you get a little window on the top of the chip, and you hit it with a little ultraviolet light. Then you cover it with a little piece of tape so it doesn't get any more exposure. And after you've hit it with the UV, it's erased. You can do that in the lab upstairs, little UV light, and you can erase it. Then when you program it, it's a nice way to store a whole bunch of memory. You can't reprogram it unless you do something physical, like hit it with the UV light again. Along comes double EEPROM. That's just like your flash drive. Your flash drive doesn't have a battery in it. Your flash drive allows electrical, erasable, programmable read-only memory so that you can rewrite the memory. Well, as it happens, double EEPROM, even the double EEPROM built into the chip of the Arduino, has a limited life. After about 100,000 writes, this stuff is no longer guaranteed to work properly, and it starts to fail. You can write a program that writes to the double EEPROM and wears it out fast. In fact, you can do the same thing to your USB drive. The reason why the USB drive is a little bit more robust is it has a chip in it which allows you to do leveling. That is to even out where the writes go, so that if you're doing a lot of writing and rewriting, it just takes the bad cells and moves them into bad block land and keeps track of them. Same thing for the SSD. Eventually, the USB drive gets worn out and it gets smaller and smaller. In the Arduino, our double EEPROM is small. It's only 1 KB. That's how big we have for our programs. And every time we download a new program, we're rewriting the double EEPROM and taking one of those cycles away. Hopefully, we're not going to rewrite it 100,000 times, but if we do in a lab situation, that Arduino is junk and must be thrown away. The chip in it must be replaced, which is the equivalent of throwing it away. So I got a company. He warrants my double EEPROM for 100,000 writes. Will it automatically fail after 150,000 writes? What do you think? Does it automatically fail? No. It might still work, but it could get smaller. And things could take a little bit longer to write out. And that is the answer to question number 19. Homework 4. So there's this idea. How do you do it? I kind of know how RAM works. Let's think about it. Let's do a deep dive into this. I'd like to understand a little bit more about RAM, ROM, and this idea of PROM, EEPROM, and double EEPROM. These are basic kinds of storage which are used inside of the computer. I want to understand how they work. How does that work? How does that work? Let us consider the lowly D flip-flop. It's able to store memory. It's not much. It stores 1 bit. That's what it does. If you lose power, what happens to the memory? It's gone, right? G-O-N-E, gone. This is volatile. What kind of RAM is this volatile RAM? This is 1 bit of RAM. That's what it is, 1 bit of RAM. What kind of RAM is that? What are the different kinds of RAM? You guys have bought it. You guys are using it now. You're using both kinds right now. Here's dynamic. And then there's static. This is static RAM because as long as power is applied, in theory, it should hold its 0 or 1. But that's different from dynamic RAM, isn't it? What's dynamic RAM? Anybody know? The dynamic RAM is based on a capacitor. We charge the RAM with a write line, and then we read the RAM with a sense line. But the problem here is capacitors have leakage. And in fact, we have a nice differential equation that shows a nice smooth curve of an exponential loss in charge for most of the capacitors. But they're much cheaper to build than these D flip-flops over here. So if I'm using them, how do I keep the charge going? And the answer is you have to refresh these. This requires a little bit more complexity. It requires refresh. That is, you have to refresh the charge in the capacitor as it leaks away before it becomes unreadable. And that's done by external means. That is to say, it could be in the chip, but it's external to the capacitor itself. So that's your RAM, static RAM and dynamic RAM. Then comes your ROM. With ROM, you can use fuses. So what you can do is you can say, look, I'll put in a fuse, then I'll blow the fuse, or not, and I'll just make an array of fuses. I'm not sure how to symbolize the fuse, so I'll just do this. And you can see how that's cheap, because all I have to do is sit there and bust out the fuses. Once I blow the fuses, the ROM has a pattern, and it will stay zeros and ones. So that's pretty good. I like that, ROM. And you can manufacture it like this over at the factory. In fact, I've built ROM out of diodes. You either put the diodes in, or you don't put the diodes in. And that enables you to create your own little ROM at home with individual discrete components. I did that in wood shop. So then, as it happens, there's a wooden thing holding it. There's another kind of ROM. We'll call it programmable read-only memory. And that enables you to blow the fuses in the field. That's field programmable. And field programmable ROM is just like a field programmable gate array. It essentially allows you to create your own little lookup table. Well, what about the EEPROM, or the double EEPROM? Let's look at that double EEPROM stuff. Double EEPROM is really rather different instruction. And to learn how the double EEPROM is working, you have to learn about it at the gate level. And what you get is silicon that has dopants in it. And the dopants either give you an excess of electrons or a deficiency of electrons. When there's an excess of electrons, we say it's a negative dopant. When it's when there's a deficiency of electrons, we say it has a positive dopant. And these go into a source line. A word line with a control gate, and then you got a float gate. Word line, control gate, float gate, and a bit line. This is all being done at the semiconductor level. And what you want to do is you want to get the control gate to allow the bit line to write into the float gate. That maintains its charge after the write line has fallen to a low level. And so with the source gate, you're able to read what's in the float gate.
Professor,
Sorry, was there a question? Yes.
the camera cut out.
Yeah, he's telling me I got a low battery, and I don't have a good way to charge it. I'm at 10% power. If it cuts out completely, we're going to have to switch to the phone. How much time do we got? Half an hour? Shoot. Yeah, I tried recording at high resolution in the other class, and I guess it consumed the battery. So this is a low-level description of how you can store a bit in the semiconductor. And it gets stored in the float gate, and then can be read. Read and written, depending upon the control gate. So that's a basic idea. There's two different kinds of double EEPROM. One is called NAND, and the other is called NOR. But both of these architectures for flash, for double EEPROM, both of them use this technique of using a float gate. Regular flash memory is called NAND memory. And that's a big seller for a lot of people. People use them for SSDs. There's a problem with them. They can only be erased in pages, also known as blocks of bytes. So this requires, you can't do I/O on the bit level. You have to do I/O at the block level. Not too bad. But what it means is that when you're looking to write out some data, you have to wait until you have enough, and then you write it out. What happens if you pull the flash drive out of your USB socket before you eject it? Well, the cache that's queuing up this block of data that it was about to write out doesn't flush. And if you don't flush the cache, you corrupt the file. That's why it's so critical for you guys to properly eject your USB flash drives. Or else what happens is the block level I/O does not finish writing out from cache, and you risk corrupting a file. If it's in the middle of a write and it doesn't finish, the file will have a improper end of file tag, and it won't be complete. If it's an exe file, it won't run. That's NAND flash. This NAND flash is what's internal to the Arduino. It's also internal to many computers, even desktop computers, because what happens is sometimes you boot the computer and you hit something like Shift F12 during the boot phase, and that gets you into a BUI menu, BIOS. And in the BUI menu, you get to set certain things, like whether or not you're overclocking your CPU, or whether or not you're going to change the boot order so that the flash drive gets booted before the CD or the SSD drive. And that goes into NAND memory, which is going to be stored inside of the desktop computer, probably in the CPU, if not in some other place where they're keeping some flash memory, small amounts of flash memory. Even things like the clock could be stored in flash memory. Although a lot of times people will provide you with a small real-time clock chip and a battery. So that's that. What about NOR? NOR flash memory, that's what people call the double EEPROM memory. They're both double EEPROM, but this is what they call it. That's the typical thing. So for the firmware for flash memory inside of your computer, you expect NAND memory. Otherwise, it would be NOR flash memory. So if you got a flash drive, that's NOR memory. Let's see what else we got here. And that's the answer, by the way, to question number 20. So we got the floating gates. That was the answer to 21. see now. One of the reasons why we're doing block level writing is that several transistors are going to be connected in series. And each one of these specialized systems is considered a separate transistor. So believe it or not, with the two different types of material, the N material, the P type, and the two legs and the gate, that's really just like a field effect transistor with the difference. And the difference is instead of a source and a drain, we're calling it a bit line and a source line. And instead of a gate, we're calling it a right level control gate with the float gate. That float gate makes the difference. So when you're looking at a typical bipolar junction transistor, things look somewhat different. This is a current-controlled current source, current-controlled current source, right? And so a little current in here changes the current that flows through here. But if you have something that looks like this, this is your gate. This could be your source and your drain. And that would be a field effect transistor. And that's what you call a voltage variable resistor. This is a current-controlled current source. That's a voltage variable resistor. And the difference between the field effect transistor and the bipolar junction transistor is the difference between using current to control and using voltage to control. And if you think about it, the difference between the FET and this little guy is a little float gate right in through here. So if you put the float gate in, you can change colors, I suppose. Put in the float gate. And what you have is an FET with a difference. And the difference is it's got a float gate and a control gate. And the whole thing is still regarded as a single transistor, but a more expensive one to fabricate and somewhat more complicated. So what happens here in fabrication in mass is you have a single bit line. And then you can write bit 0, write bit 1, write bit 2, da, 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 da. In other words, you have to write several of the transistors at the same time from the different write bits. Once this bit line says, yes, it's time to start to write to the float gate. And that's why you have to essentially write multiple bits all at the same time with this technology. It's just a hack. And that's typical for NAND memory. You'd see several transistors connected in series. So series NAND memory. And that's typical for flash memory. And you can see why they would do that, right? Because it reduces the total number of connections. And that gives you an answer to question 22. Can you erase any single bit that you want to in NAND memory? Suppose you wanted to erase bit 1. Would you be able to do that in NAND memory? No? Why not? Just find out what the bits are, clear this bit, rewrite them. You'll have to rewrite them all. But in the process, one of them could be zeroed out. So if you're willing to rewrite them all, yes, you can erase individual bits. That's the answer to question 23. This is interesting stuff, right? Because you're getting into the weeds of different kinds of memory. You may not have encountered this before in Digital Design 1. In fact, I don't think we teach it at all in Digital Design 1, but that's all right. Can't teach everything, especially in the first class. And you're probably going to encounter flash memory more and more. I must tell you that I'm quite surprised at how dense flash memory drives have become. I mean, 128 gig drives are not that uncommon now. And it's certainly possible to buy 256 gig drives if you're willing to spend the money even higher. So it's not, I mean, it's not only not that expensive, it's well within the realm of, I guess, undergraduate students to afford, right? People here will probably be buying, I don't know, terabyte flash drives before they graduate, I would guess. But right now, buying a 256 gigabyte flash drive is perhaps a $40 item. And I don't think that's all that expensive. It sounds terribly cheap to me. It's a lot of storage. And it's not like you have to go far to find it either. I think you get them on Amazon and they get them to you overnight or something, or a day or two. Sometimes people have laws. You ever noticed about the laws? Here's a law. You like this law. Force equals mass times acceleration. That's like a law, isn't it? And that works until it doesn't work. Like when you go at relativistic speeds, then all of a sudden you have to think about Einstein and other stuff. So yeah, it works mostly. So it's not quite a law, but it's a good rule of thumb. And it's a nice, convenient way to model stuff. Computer architecture has this too, right? The physicists have convenient little laws. Here's one called Amdahl's law. And the book goes into this at some length. It's a convenient rule of thumb. It's not like, oh, if I break Amdahl's law, I'm going to Amdahl jail or something. So here comes latency as a function of S is equal to 1 over 1 minus P plus P over S. So P stands for the proportion of execution time that is parallelized. So this is the part that is concurrent. So I think that's the best. I don't parallelize, it's proper English. Let's call it, that's the concurrent part. So if I could parallelize 90% of the program, I should be able to realize some kind of a speed up, the change in latency. S is the speed up of the task that benefits from the improved system resource, and latency is the theoretical speed up of the execution of the whole task. So that's interesting, right? Let's think about this. Suppose I had a speed up with, I don't know, we'll call it 10 processors. I would have expected the overall speed up of the system to go up by a factor of 10. But that's not going to happen, is it? Because there's some part of the task that's not going to be able to benefit from that speed up. Suppose I said to you, I've got a way to identify which part of my code is slow. I can do that, right? I call it profiling. So I like that. I run my program and I profile. When I profile the code, it tells me where is it slow. And then I can focus my efforts on making that part of the program faster. That's sensible, right? There's a program that I use. It's called ray tracing, right? It renders beautiful graphics. And it spends 90% of its time doing a ray object intersection. And the ray is like a ray of light. And it has to fire lots of rays. Each time it runs into another pixel, it fires and it gets another, oh, I lost my video here. It fires more rays. No, we lost the video. Sorry about that. I just noticed. So you guys got to tell me when that happens. I got 5% power left. I think I can make it for another 10 minutes. So 90% of the program's time is spent doing CPU intersection. So let P equal 90% of where I spend my time. And now I'm going to get my 10 processors, and I'm going to get a speed up of a factor of 10. Wow, that sounds good. So now what I'm going to do is I'm going to take my 90%, 1 minus 0.9. That's this part. I'm going to take the 0.9, and I'm going to say, I got a 10 times speed up over here. How much faster am I really going? Let's make a little experiment out of it. So now I got 1 out of 1, let's see, we'll call it 0.1 plus, what is this, 9/10 over 10, which is probably 0.9, something like that. And so my speed up is really only 1 over 1. I didn't really get much speed up at all. So what happened? I kind of canceled it out. I didn't do better. Why not? Did I do this wrong? Amdahl's law tells us that if you're only speeding up some chunk of the program, all of a sudden the other part of the program tends to dominate the computation. And so my theoretical speed up is not really yielded very much in the way of benefit, because I couldn't speed up the whole code. There was still some part of the code that was going to slow me down. I think there's something wrong with my computation there, but you get the idea. And the way it goes is in the limit, as you start to look at these things, even when the speed up goes to infinity, you're limited by this. And that's the limit. So if I can speed up some 90% of the task, I can't really do a whole bunch better than my upper limit, my theoretic upper limit, because there's still a part of this which is going to be 1. So maybe I can get a 10x speed up with 10 processors, but that's about the best you can expect. And if you have a substantial fraction that takes away from that, you're not going to be able to do better. So that's this guarantee. You go 10x better on 90% of it, you're still not going to do more than 10x better on the whole system, and you'll do substantially worse. I'm about to lose power again. I am down to 4% here. So there's a section in the book on Amdahl's law, and I encourage you to read that. And what we just covered here was really question number 1 and 2 in homework number 3, homework 4. What I kind of wanted to do was a little bit more in the area of translate look-aside buffers. But I don't have the time to do that right now. It's a bigger topic than I care to be able to get into. And so I think what we're going to do is call it quits just a few minutes early, especially because I'm about to run out of power for the distance learning folks. And there are many of them. Let me just check. Oh yeah, we got a lot of people online here. So I don't want to lose the class in the middle of this, and I think I'm about to. So let's call it quits for now. Thanks a bunch, and try and stay safe. When you go home, see if you can read a little bit more about the translate look-aside buffers, and we'll cover that next time. Have a good day.
Thank you.
Thank you.